Alright, so now we're going to be talking about linear transformations and mapping, which is one of the most important parts of linear algebra. So, just to begin with, there are there are three different types of transformations that we could have in general. Uh, so we could have transformation from a higher dimension to a lower dimension, from a lower dimension to a higher dimension, and of course a transformation within the same dimension. Now, we must note that when we transform within the same dimension, it is known as a translation or a transition. And we're going to talk about two main methods of doing transformations. One of them requires one of them is a matrix diagram method, which specifically applies for isomorphism. And then, of course, there's a general method that we use that could apply to any type of transformation. So for our first example here, we're going to be talking about transforming from a higher dimension to a lower dimension. So what we're given is a transformation equation, which is some function of the coordinates, essentially. We're given a vector in standard bases, and we're given the basis b and b prime. So the basis b is a basis that spans a vector space that we are going to be transforming from, whereas b prime is the standard basis that represents a vector space that we're transforming to. And the question asks us to specifically solve for the transformation matrix A, the transformation of V, T of V, and the transformation of V in the basis of B prime. So we start this off by solving for the transformation matrix A, and in order to get this matrix, we transform each of the standard bases and put it in terms of B prime. So the columns of A, each of the columns of A corresponds to the vectors that we obtain from transforming the standard bases in column form. So as we could see, A is equal to negative 5, 2, which corresponds to vector negative 5, 2, and so on. Now to get VB, in order to solve for VB, we first have to transform in order to get to VB, we start off with the standard basis and put it in terms of B, in terms of the standard basis of B. So in order to do that, we know that it is just some linear combination of the three orthogonal vectors that span that space, and that gives us negative 0.5, 0.5, and 1.5. In order to get TVB prime, we multiply the transformation matrix to the vector that we had in standard basis in terms of B, and we get the resultant vector negative 12, 5, and then if we convert this back into standard basis, that would simply just be 3, 5. In order to convert it back to standard basis, we just multiply each of the coordinates to their corresponding basis. Now for our next example, we're moving from lower dimensions to higher dimensions, and we're given another transformation equation. So we're given x minus y, 0, x plus y. We're given another vector in standard basis, negative 3, 2. We're given the basis of b and b prime, as can be seen, and we're solving for matrix A, the transformation matrix, TV, and TVB prime. And the process is pretty much the same. We start off by transforming the standard bases and putting them in terms of in terms of B prime. And we form the transformation matrix out of this. And then we convert our vector to from standard basis to the basis of B, which is again the vector space we're transforming from. And once we do that, it's pretty simple. We just multiply the transformation matrix to that vector, and we end up with our transformation vector in terms of B prime. And then we can bring it back to standard form by expanding it out and multiplying each of the coordinates to the corresponding standard basis. Now, isomorphism, as we talked about earlier, can be done using the matrix diagram method. But first, we must start off by defining what an isomorphism is. And as we mentioned earlier, an isomorphism is a linear transformation that occurs within the same dimension. Now, one thing to note about this is that aside from following the same rules as linear transformations, such as being closed under scalar multiplication and addition, there are there's two other important components in order to make a transformation and isomorphism. And one of them is that the transformation must be onto, which means that each vector in the space that you're transforming from has a corresponding vector in the it has an image in the space that we're transforming to. So and then of course it has to include 0, which is again which is one of the properties of linear transformations in general. And our example here is we're given the transformation equation 2x minus y comma x, and we're given VB, and we're given the basis of B, and we're given the basis of B prime, and we're asked to solve for the matrix, the transformation matrix, P inverse P and T VB prime, and I'll explain what these are in a minute. So P is simply just the transformation from VB prime to VB. A is the transformation matrix is just simply A, and this diagram over here demonstrates how the route that we're going to take for the transformation. So the transformation from VB prime to VB is going to involve vector P or matrix P. From VB to T of VB is going to use the matrix A, and then from TVB to TVB prime is going to use the matrix P inverse. And we're going to show you how to do that real quick. So first thing we do is set up the transformation matrix, and this is a matrix in row form where the left column is simply just the x is the coefficients of the x, whereas the column on the right side is the coefficient of the y, and the top row corresponds to the x coordinate of the transformation equation, and the bottom row corresponds to the y coordinate, so the function that's in each of those coordinates. So in order to solve for P inverse, we make an augmented matrix, and we set it up such that on the left side we have the standard bases in column form of the matrix of the vector space that we're transforming to, which is B prime, and on the right side we have the standard bases of the vector space we're transforming from. And in order to calculate P inverse, simply we are just going to we're just going to put an identity in the basis that we're transforming from, so that would be B prime, transforming to, so that would be B prime, and then that will give us the reverse transformation, which is basically from B prime to B, and that would simply just be -2, -1, -3, 1. We multiply this by vector VB prime, and that gives us -7, 3. So that is the transformation from T. That is a transformation from VB prime to VB. So from here we're going to go from VB to TVB, and in order to do that, we take the same vector VB, and we take the transformation matrix. We multiply to the vector VB, and we get TVB, and then we move downwards to TVB prime. So we multiply it by the inverse of P inverse, which is P. So we multiply the matrix P, which is 1, -1, 3, -2, and we multiply that to vector TVB, and that gives us our final answer, TVB prime, which is -38, -31.